bit about myself, first of all. I'm probably one of the people that have been working on the PRT concept the longest. Not the longest in this room. There is somebody else in this room that I'm going to tell you about that's been in longer than me. But I worked on the original control system for the Morgantown PRT. So I have a fairly good understanding of what it took to control them. I actually have quite a thorough understanding of what it took to control the Morgantown PRT system. But beyond that, I've been doing PRT control development type work for pretty much 40 years now. Following the Morgantown project, which ended around 1980, I was working then for the Boeing aerospace industry, and the Boeing company got a contract from the Urban Mass Transit Administration to do a research and development project to develop what they call the AGRT program, Advanced Group Rapid Transit. The objective of that program being to develop a 3-second headway control technology for GRT. And back then, the program manager was Mr. Walt Kulik, sitting there on the end of that role. So that's why I say he's probably been working at it longer than I have. But yeah, Walt and I go back a long ways. Back in 1984 then, I went to work for the Bay Area Rapid Transit, San Francisco Bay Area Rapid Transit. Those of you who know the San Francisco Bay Area, that's the major subway system in San Francisco. Today they carry about 500,000 passengers per day. They have a fleet of about 700 vehicles and over 100 miles of track. My work there was to manage the train control engineering department. And that's what I was initially doing. But then the last 17 years of my 25 years at BART, I managed what they call the Research and Development Division. So as part of Research and Development, we were always tasked to kind of find the next generation technology that can help BART become a better BART. And of course, since my background was in control, our biggest project was a train control development project. So I applied for a grant from the Federal Transit Administration, received a $20 million grant to develop a radio-based control system for the San Francisco Bay Area Rapid Transit. That too was managed by, well, the money came from ARPA, actually, Advanced Research Project Agency, but it was managed by the FTA. So again, I had very close ties with my friends at the FTA. Now, that technology that we developed there at BART was subsequently licensed by a company in Japan, and they have now deployed it in Beijing. It also runs trains in Sao Paulo, a city in India, and someplace in South Korea. All this to say that, I've been working in this field of vehicular control for a long, long time. Doesn't necessarily make me an expert, but I've got a lot of scars and a lot of white hairs to prove it. Yeah. So, our company is called Transit Control Solutions, and we've been developing vehicle control software that targets application for, I would say, large scale and regional ATN systems. I heard the word the other day that scalability is important. You've got to be able to build ATN systems that can not only connect your local network, but also the local network can be connected to an adjacent network, and that network can then be connected to another network, and eventually maybe connect to a big metropolitan area. That's what our focus has been, is to develop a control technology that can provide that kind of connectivity. Now, 3 years ago in Podcar City 7, I believe it was, that was held in Washington, D.C., I stood before you, and I don't know who among here was there at the time, but I explained or announced to you that we were going to be building a scale model of the system with this control software that we were going to be developing. I have to apologize because it's been 3 years now, and for 3 years I kind of disappeared off the scene. That was because at the time I didn't know that as soon as I returned back to San Francisco from the conference in Washington, D.C., I was met with a request to help a major U.S. transit agency address a operational safety problem. And I spent two and a half years totally distracted from the PRT interests. So that's why, after announcing that we were going to do something 3 years ago, it's now 3 years later, and I'm just now coming back to report on progress. But about a year ago, we started out and we said, well, scale model is nice because you get to kick the tires a little bit. Although if you kick the tires on this scale model, you would break it. What would be more useful would be an emulation model. Something that basically runs the code that would run a real system, but run it all inside of a computer, so that you can see how the real software would run when stressed with lots of vehicles, lots of track, lots of passengers, whatever the input parameters that you want to put into it. So we set out writing what I would call emulation code as opposed to simulation code. And with that, we were able to see how vehicles would move. We had a computer model of the vehicle, and there's an object in code. And we could see how we could have hundreds of vehicles running, and we could see how those vehicles would run, collect data on how many vehicle miles were used, were consumed, what the average wait time was, what the average trip time was. All that kind of statistics would be collected from this. In addition, it was useful. We think it will be useful to use as a tool to understand whether or not you've designed your stations correctly. Are your ramps long enough? Do you have enough berths? Things like that can be studied with something like this. But after we wrote the emulation code, we looked at it and said, gee, this is emulation code. It's running as close as we can model a real vehicle. If we had a vehicle, we could actually run the vehicle. So that's why we said, well, I did promise to make a scale model 3 years ago, or at that time 2 years ago. So maybe I should follow through on my promise and do this. So we did eventually go out and, since my business is not building cars, I wasn't going to design my own car. We went out and bought some toys and put a little computer and some toys, built a little track, and then ran our emulator against with the toys. And that's what I'm going to show. At the end, I'm going to show a little video of that. But some things about our control system here. To be scalable, we felt that what was key was that we achieved very high capacities at very high speeds. Those are contradictory parameters for a control technology, because as we saw earlier, there's a bathtub curve effect. The faster you go, the further behind you have to make the car follow. But that's what we've tried. That's what our control logic is trying to address. How do you achieve low headways at high speeds? So I would say that we can achieve headways that are less than what you can achieve with moving block control technology. In essence, roughly on the order of less than 1 second at at a speed of about 60 miles per hour or 96 kilometers per hour. We think this leads to scalable PRT systems or PRT networks. And we've been encouraged to make it an open architecture solution so that others can contribute to it. I believe that ultimately anybody can add their own empty vehicle management algorithm to it, and we can run it with that empty vehicle management algorithm. You probably don't want to hack into the safety critical code, but everything else in there, I think that we'll provide the interfaces, and if people want to participate, I think it can be made available. Let's see. So some other key characteristics. This is really important. What we've developed here is based on fail-safe. I use the word fail-safe, but basically in the rail industry we would call it vital, or fail-safe essentially. Nothing can fail on it and cause, again in the rail industry terms, a permissive result to occur. When a car is supposed to stop, we will never generate a go command, or we will always generate the most safest output under all circumstances. And when the failure occurs, that causes you to, when any failure occurs, that first failure will always be detected. That allows you to go in and replace and repair whatever that component is. Another characteristic of our system is that we, in advance, pre-calculate the precise movement of the vehicles, and then make the vehicles follow those trajectories. We also, given a track network, we find ways to achieve conflict-free operation from origin to destination station, so that as we go along, we don't have to slow down too much or speed up too much. We can schedule our system so that when you arrive at potential conflict points, cars are arriving at such time that it's not going to be conflicting with other traffic. The functional allocation, this is probably similar to anybody's control technology. We have the 3 levels of control. And control we view as a non-safety critical function. I'll explain in a moment. But the supervisory level, which is the level that provides the fleet management. Where do we want the cars to go? how do we want to schedule the behavior of the system. The control level, this is where we do the computation of precisely what we want the cars to do. And the actual physical level, which actually controls the motion of the vehicles. And this is what causes the vehicles to track the trajectory commands that we generate. And then completely separate from the control level, we have a separate module, which we call the safety monitor. And this has only one responsibility, which is to watch the cars moving around, make sure that they're never doing something that's unsafe. And if it does something unsafe, basically pull the plug so that the train cars are brought to. I keep saying train because having worked at BART, my mind is train oriented. But so basically, it's fail-safe collision avoidance. I throw this up there because this is the track we use to kind of test our emulation, so that we can test whether or not what we built is doing what we thought it was. So, given a track like this, let's say your objective is to send the car from the starting location to some destination station. Well, the system route manager, or the level that does the supervisory work, would then find a path, which in this case would be the yellow line. And in some cases there could be multiple paths. In this case there's only one. Find the path that goes from origin to destination station, and then identify where all the merge points are. Here we have 1, 2, 3, 4 merge points. And look to see whether or not there are other conflicting traffic going to those locations. If not, it would then tell the vehicle, it would tell the controller, these are times that are free. You can occupy the merge points at these times. And the control level would then calculate how to get the vehicle to those merge points at the right time. At the physical level, this is where the closed-loop feedback control comes into play to make sure that the car tracks the trajectory and goes exactly as it's been told to go. Now, on a network of this size, I think that it's probably quite doable to schedule that traffic all the way from origin to destination. But as the network gets larger and larger, it may not be practical to find a clear path all the way to the end at the beginning of the run. So the other thing we can do is we can reserve merge points one jump at a time, so that when you initiate, we make sure that we have clear path through merge 1, then we look for a clear path through merge 2, and then just kind of move our way through. So whether you have 4 merge points or 100 merge points, we're just reserving our path one path at a time. Let's see what comes up after this. So the basic point being that we think that with the capabilities of what we show here, that you can begin thinking about ATNs as being more than a first mile, last mile solution. Because with the performance that you can achieve with our ATN controller, at the higher speed, you can achieve higher line capacities. And therefore, you can envision a future in which regional networks can develop, where you have one community with a local network, another community with their local network, another community with their local network, and then you can begin to build these higher speed lines that travel the longer distances and achieve the line capacities you'll need to be able to support that traffic between community to community. So that's what we've been trying to target with the work that we've been doing. The current status is that, as I explained, we built our emulation code. We built this small scale model. I'll show you in a moment. We field tested our tracking sensor, vehicle tracking sensors, and our wireless data communication technology. Several patents have been awarded. We have many more in patent pending. And we like to discuss licensing if anybody's interested in using any of this at some point. We are in discussion with some of you already. But if you have any questions you want to ask, this is a question I want you to ask. How do we license for it? So I want to show a quick a scale model. It's a two-minute video. Hopefully I have time for that. I'd like to say, though, I've seen some awesome videos this weekend. The InVideo, that's awesome. Ollie, the Ollie car, Matthew, that was awesome. In Citra, they're so I'm a little bit embarrassed to show this. In fact, I want to crawl under the table and hide when I show this, because it's literally a toy. But I will say this, we did borrow from the auto industry like everybody else seems to be doing today, because the cars that you're going to see originally had 69 Dodge Charger car bodies on them. And we just took the that car body off and put a little PRT-like car body on. Melody is my daughter-in-law, so I have to say, in order to create this video, I had to have a son, I had to raise him to adulthood, I had to marry a nice young lady, waited until she graduated from Juilliard School of Music, a very famous music school in New York, for her to compose this. So, and on top of that, she composed this based on a painting that her grandmother drew, and her grandfather wrote a poem for. And that's what inspired her to write this music. So I think I've been working on this for 70 years plus now. Now beat that, NVIDIA.